So looking at page 13, we're asked to use the properties to evaluate some integrals. So these integrals are given with integrands that are in general form. So we have f of x going from 0 to 3 giving an area of 4, going from 3 to 6 giving an area of -1. Right? So one of our properties allows us to take the sum of those two integrals. So for example, if I were to take 0 to 3 of f of x dx and add to it 3 to 6, that would give me 0 to 6. 0 to 3, then 3 to 6. Put it all together, 0 to 6. So 0 to 3 has an area of 4. 3 to 6 has an area of -1. 4 plus -1 is going to give you a 3. All right. 6 to 3 is the opposite of 3 to 6. So one of our rules states that we can swap the bounds of integration as long as we negate the integral. So I have the negative in front of the integral, but 3 to 6 for f of x dx gives you a -1. So -1 gives you a 1. C is pretty easy because if you're not going anywhere, you're not going to collect any areas. Then D, still going from 3 to 6, but now we have a constant multiple, so I can factor that out. -5, 3 to 6, f of x dx. So I'm going to have -5 multiplied by, it says right there that from 3 to 6, f of x dx is -1, so -5 times -1 is going to be equal to 5. All right, so that's example 1. Example 2, given region A has an area of 1.5. All right, so has an area of 1.5, but that's below the x-axis. So they must be talking about a negative area. All right, so, well, its area is 1.5, but the integral must be negative, I should say. So from this, we can now conclude that over the interval of 0, or the interval of 0 to 2, f of x dx must have an integral of -1.5. All right, 0 to 6, that's given as 3.5. All right, so that's just by looking at the graph. Now, in part A, part A happens to be the thing we just figured out, so that's good. -1.5. For part B, 0 to 6, but the sum of a constant and a function. So I'm going to take 0 to 6 of 2 and add to that 0 to 6 of f of x dx. All right. So if you anti-differentiate a constant, you're going to get the variable multiplied by that constant, so 2x. And then we could apply the fundamental theorem and figure it out that way. But we could also just kind of look at it in the context of areas. This is the same as saying, and I could just kind of pull this off on the side here, 0 to 6 of 2 dx. If I create a quick graph, this is some function. In this case, y equals 2, horizontal line. Going from x equals 0 to x equals 6. So the question's really asking, what's the area of that rectangle? Well, it has a base value of 6 and a height of 2, so it must have an area of 12. So a nifty little shortcut when it comes to constants is if you find the difference between the boundaries of integration you just multiply that by the integrand and you have it. All right, so the 12 multiplied by the 3, added to the 3.5 is going to give me 15.5. For C, it's saying what's the absolute value of the integral of the absolute value of the function. Now, I gotta say, in all honesty, it wasn't until I became a teacher that I learned or recognized that, yeah, absolute values, yeah, it tells you to drop the negative for a number, but it's really just telling you to bring anything that is negative into the realm of positives. Right? So anything below the x-axis should be reflected to be above the x-axis. Right? So a graph of an absolute value function is really just, it's very similar to the graph of the function itself, except any part that's negative gets reflected to be positive. So this piece would now come into existence replacing this piece. All right, I'm not really going to X that out because it still exists, but that's what we would be looking at when we're talking about the absolute value of f. So I'm going to kind of accentuate that. So this whole curve, well, maybe I'll make it a little thicker. This might be a little too thick, we'll see. This curve in red, that's the absolute value of f of x. All right, so somehow I made it through all of my education as a student without ever recognizing that. All right, so this is me hoping that I can help you avoid that. All right, so the area that we'd be looking for would be the area contained here, which we know is 1.5 based off of symmetry. And we'd have to add that to the area here, which we don't yet know. All right, but what we do know is that if we take A, region A, and add to it region B, that would give us the integral over the interval of 0 to 6 of f of x dx. We knew that A was negative 1.5. The B is the part that we would be looking for. That's the integral over the interval of 2 to 6 f of x dx. And 0 to 6, that's 3.5. So just by solving this equation, we can determine that going from 2 to 6 would be 5 units. All right, so we now know that this piece here has to be equivalent to 5. Add them together, and you get the result of 6.5. All right, so that one's a little tricky. Some of the other ones not too bad. That one's pretty tricky. All right. The negative 2, factor that out. Need to replace the integral with what we know it to be, which is the negative 1.5. So this, we discovered its value to up here. Alright, so negative 1.5 multiplied by the negative 2 gives us a final answer of 3. So there we have it. Alright, well, the last little bit here is the average value of f. So an average value is based on, well, there's a formula, but it's basically going to simplify it down to the concept of a mean. Alright, so it's the average area over the interval. So with that in mind, it's kind of along the lines of saying, all right, well, if you know what the area is, and you know what the length of the region is, then you pretty much have it. So the formula, though, is 1 over b minus a. That's the length of the region, multiplied by the integral over the interval of a to b of f of x dx. So in this context, it would be 1 over 6 minus 0, so this is our a, this is our b, from 0 to 6 of f of x dx. So 1/6 of whatever the integral is over the interval of 0 to 6, which right in the beginning they told us was 3.5. So 3.5 over 6 is going to be 7/12.